In this video, we will talk about ideal gases, the internal energy of gases, and the Maxwell-Boltzmann distribution. So to kick this off, let's mention that gases can be compressed, unlike solids and liquids. So this means that we can reduce the volume of a gas, okay? This cannot be done with a solid in general, okay? And in the development of thermodynamics, various laws were discovered concerning their behavior as pressure, volume, the number of particles, and temperature vary. So what I mean by that is that, for example, there were experiments in which someone kept the temperature of a gas constant and they changed the pressure and saw how volume changes when you do that, and so on and so forth. I'm going to talk about those experiments later, but for now, let's mention that all laws can be expressed or culminated pretty much to the most famous equation when it comes to thermodynamics and gases, pretty much given by pressure times volume equal to the number of particles n times kb. This is the Boltzmann's constant, and nt. Okay, so pressure is measured in pascals, which is equal to newtons per square meter. Volume is measured in cubic meters. Temperature is measured in kelvins. Here we need to use kelvins, by the way, not Celsius. I'm going to talk about kb later, but it has units of joules per Kelvin. And n is a pure number, okay? For example, if we have 1 billion particles, n is just 1 billion. It doesn't have units, okay? It's dimensionless. Now, kb is given by 1.38 times 10 to the negative 23 joules per Kelvin, okay? One thing that is seldom discussed is that notice that P times V has units of pascals. Actually, let me use red since I used red earlier. So pascals times cubic meters, which is nothing than newtons per meter squared times meters cubed. And this has units of joules, guys. And we can also see this from the right-hand side of this equation. If we substitute units for the right-hand side, we have n, it's a pure number, and then we have kb, which has units of joules per Kelvin, times Kelvin. We also get joules. So this equation has units of energy, pretty much. Also, I want you to notice that, not to notice, I need you to be aware that n, the number of particles, is in general very large and proportional to Avogadro's number, pretty much, 10 to the 23 particles. Okay, I'm gonna come to Avogadro's number, but also let's add that because the number of moles of a substance is given by, and this is from chemistry, by the way, is given by the number of particles over Avogadro's number, and because Kb is defined as R over Na, where R is the ideal gas constant. I'm gonna write it later. We can also write PV equal to N times Na times R over Na times T. So another expression for the ideal gas law. By the way, I forgot to mention that PV equals to NKT is the ideal gas law. Okay, so PV is also equal to nRT, where n is the number of moles now of a substance. Na is Avogadro's number, equal to 6.022 times 10 to the 23 particles per mole, and R is 8.31 joules per Kelvin per mole. Okay, and this is the ideal gas constant. Now, a natural question that rises here is, why is P times V equal to N kBT? How did this come to be? So we will examine how this conclusion was met macroscopically. So macroscopically means by examining properties such as pressure, volume, and temperature. These are properties of the gas as a whole, whereas microscopically will be examining the behavior of the gas by looking into individual molecules and atoms inside the gas. Okay, so the first attempt to explain gases was Boyle's law. So this came by Boyle. So he examined he checked how volume changes as we change temperature, as we change pressure at constant temperature. Okay, so to do that, he used a piston, okay, sealed with some lead that had a surface area A. Okay, he put some mass on top of this piston, so this is some mass M. Therefore, the pressure is equal to the weight of applied on the piston over the surface area, or M times G over A. And he kept the temperature constant. Okay, so how did he do that? He didn't change the temperature, pretty much, I guess. So what he found was that P is proportional to 1 over the volume. If we plot that, it will look something like P. If we have P and V, it will look like this at some temperature T1. And maybe if he applied some heat, okay, maybe he used a Bunsen burner or something like that to apply some heat. So if we apply some heat and raise the temperature to T2, okay, let's go back to this. If we raise the temperature, what's going to happen? We will get a curve parallel to the first one, but higher up the diagram. So you see how for the same volume, we get higher pressure at higher temperature, which kind of makes sense if you think about it intuitively. So this arrow represents a change in temperature. So if we have a curve up here at T3, we immediately know that T3 is larger than T2 and larger than T1. Okay, so there is a cool simulation I want to show you at this point. So let's go away from the notes and into the simulation. Okay, guys, this is the simulation I want to show you, and I'm going to provide the link to this simulation in the video description. So it's from the University of Colorado, again, the PhET simulations. I think it stands for Physics Education Technology or something like that. So let's add some gas using this pump into this container, and notice how the pressure changes. And by default, they have the temperature staying constant in this scenario. Okay, so we cannot change the pressure in the simulation. We can change the volume. Okay, we can use this handle here, you see. So if I reduce the volume, notice how the pressure increases, and if I increase the volume, the pressure drops. Okay, so these quantities are inversely proportional to each other. I mean, you can see it using the lid, right? And let's see what's going to happen if we change the temperature. Okay, we keep the volume constant and we change the temperature. Okay, So you immediately see how the pressure changes. Why? Because particles move faster now, and you can see it visually, okay, how they come faster, okay? And because they move faster, they have more collisions with the container, therefore the pressure increases, okay? And you can play more with this simulation. Let's see. We can also add light particles. Okay, so you can have a mixture, I guess, of two gases. Okay, this is interesting. But anyway, I'm gonna leave it here, and please experiment with it, etc. So you can change this lid. You can also measure the width, I think, yes, of the container. So maybe you can do calculations. So they give you that the length here is 11.3 nanometers. So that's actually the width. And the length is somewhere there. So you can maybe do some calculations if you like. Get creative, guys, and play with it. So yeah, let's go back to the notes. The second investigation or law that was discovered about ideal gases was from Charles. So let me use black. So Charles' law. So he kept the pressure constant and varied volume and temperature pretty much. So his setup looked like this. We have our piston closed by some lid, and we apply some force in the form of a weight. So pressure is m times g over the surface area of the lid, and it's kept constant, so we don't add additional mass. What we do instead is to allow this lid to move as we heat up. So we have a heat source, okay, that can change the temperature of this gas, okay? And I'm not going to show you the simulation again, but the idea is that if you increase the temperature, the lid is going to move up, the volume will increase, okay? And vice versa. So if you plot the findings, he found something like this. If we plot volume versus temperature, we will find a straight line, okay? That maybe looks like this, okay? So he found pretty much that volume is proportional to temperature. And this is an important law because this was the first time in which people tried to extrapolate this graph, okay? And if you extrapolate it, you can find, so extrapolate to 0. And what kind of 0 is this? It's the absolute 0 of the temperature. So this was the first time in which they determined experimentally, and again, macroscopically, that there is an absolute temperature, an absolute 0 of the temperature. So, by the way, I mean, in the conditions that Charles had in his possession at the time, maybe this was like 350 Kelvin, for example, okay? So what I'm trying to say is that these measurements maybe go from 350 to 450 or something like that, okay? And he took multiple measurements within that interval. And then if you extrapolate this, because it's a straight line, okay, you figure out that there is a 0 that it's minus 273 degrees Celsius from 0 degrees Celsius, okay? So this is Charles' law. He found that if we keep the pressure constant, so at P constant, volume is proportional to temperature, okay? And I think this is the last law, yeah, we will talk about. The next law is called Gay-Lussac law, okay? So in this law, in this experiment, in this setup, they kept the volume constant pretty much. They varied the temperature and they measured the pressure. So their setup looked something like this, okay? So here we have a barometer, that's how it's called, an instrument that can measure pressure, okay? So pressure measurement is done using that instrument, pressure measurement. Okay, this is a closed container containing some gas. Let's use let's use red dots to represent our gas. So that's the gas, and we have a burner, and the volume. So volume is constant. Okay, and we can increase the temperature. Okay, we can vary the temperature. So this setup allows us to vary the temperature and measure the pressure as we keep the volume constant. And what they found was, if you plot pressure versus volume, you find a straight line. Okay, so pressure is proportional. Sorry, guys, this is temperature. Okay, so they found that pressure is proportional to T, to the temperature. Okay, keeping the volume constant. So add V equal to constant. Give me a second. P is proportional to temperature. So if we combine all laws, so pressure proportional to temperature, volume proportional to temperature, and pressure proportional to 1 over V. If we combine all of these, we get PV equals to NKB T. Okay? And a bonus is that at 0 degrees Kelvin, there is no motion for particles. Okay, and this is the macroscopic derivation of the ideal gas law. Okay, and again, macroscopic means examine global properties of the gas. And these are pressure, volume, the number of particles, and temperature. Okay. Before moving on, let's talk about some tricks we can use. So, tricks related to PV equal to NKT or nRT. Okay, both can be used. So let's take the case where the temperature is kept constant. Okay, so constant T. This is called isothermic. Okay, it's a Greek word meaning at equal temperatures. Okay, so if we have some gas, actually, if we use the graph, maybe it's helpful. So let's say that we have some gas at some pressure P1 and some volume V1 undergoing maybe an expansion, okay, and in which the pressure drops and the volume increases, okay. So this is a constant T process, okay. So we can use the ideal gas law for P1 V1. We know that P1 V1 is NK T1, okay? And we also know that P2 V2 is NK T2. And it's the same as before because we are dealing with the same gas. We are not losing particles or gaining particles. K is the same as a constant, and T1 is equal to T2, right? So we can divide these two to find that P1 V1 over P2 V2 is equal to 1. Okay, this cancels, and T1 and T2 are equal, so we can cancel them. So we immediately find that P1 V1 is equal to P2 V2. Okay, and this is for constant temperature, so this is for an isothermic process. Let's go see another example. Let's say that we keep pressure constant. So if P is constant, then we can solve for P to find that this is a different process, by the way. It's not it's a new process. It doesn't have to do with the previous one. So so don't look at the graph. This is what I'm trying to say. Okay. So if we solve the ideal gas law equation for P, we find that P is nRT over V. Okay. So if they tell us that the pressure is constant, then we have that P is maybe nRT1 over V1, and this is also equal to nRT2 over V2. okay, because the pressure is constant. So we can set these two equations equal to immediately find that T1 over V1 is equal to T2 over V2 for P constant. And by the way, this is called an isobar, okay? It's called an isobaric process, pretty much, okay? Which means at constant pressure. Now, what happens if the volume is kept constant? So if V is constant, and this is called an isochoric process, then notice that V, we can solve the ideal gas law for V. So V is nRT over P. So maybe we can use that V is nRT1 over P1 and also equal to nRT2 over P2, okay? So for this case, we find that T1 over P1 is equal to T2 over P2, okay? In all these processes we discussed, note that in all these processes, we assumed that N is constant, or little n is constant, the number of moles, okay? So we keep the number of particles constant. We don't lose or add particles, okay? Because if we did that, things change. So these are three nifty properties of ideal gases you can use when things are kept constant, okay? Okay, now let's move on and see things from a different perspective. And let's talk about the kinetic theory of gases. Okay, so let's repeat the ideal gas law. PV is nKT was proven macroscopically. When I say was proven, I don't mean by us. I mean we demonstrated how people came to this conclusion about the ideal gas law, and they had no better alternative at the time because at the time they didn't know anything about the existence of atoms and molecules, but we do now, okay? So PV equals nKT was proven macroscopically, but it can also be proven microscopically. And when we say microscopically, we mean by examining the individual motion of particles within a gas. So in fact, we can prove that PV is 1/3 times the number of particles times the mass of these particles times this quantity in brackets called c squared. Now, what is that? So actually the square root of this quantity c squared in brackets is called the root mean squared speed of a gas molecule. Okay, so, and therefore the quantity in brackets c squared is the mean squared speed, which is the mean speed of a gas molecule. So now we are talking about an individual gas molecule, okay? So we can combine this equation. So this quantity here, this equation here, PV equals to 1/3 N times M times C squared can be proven microscopically. And I will provide the proof. It's optional. You don't need to know that. You only need to know this, okay? So combining this with the ideal gas law over here, okay, we immediately find that nKT is equal to 1/3 N times M times this average quantity squared N cancels, okay? So we can show that m times c squared is equal to 3 kt, and I'm gonna stick a 1/2 in front of everything. 1/2 m c squared is equal to 3/2 kt. Okay, so why did I stick this 1/2 there? Because I want to reveal this equation here, which gives you the average kinetic energy for a gas molecule. Oops, nice spelling there. Molecule. And recall that 1/2 mv squared is the kinetic energy of some mass moving with some velocity v. So 1/2 mc squared is the average kinetic energy for one molecule. That dash up there means average kinetic energy. Okay? So remember when we said that heat translates to increasing the temperature and temperature translates to motion? This is exactly shown. This is exactly what we see here. If we increase the temperature, so if T increases, this average squared speed of molecules also increases. Okay? So to derive this equation, and by this I mean this equation, okay? This one over here. Okay, to derive that equation, we make the following assumptions. So, to derive PV equals to 1/3 NMC squared, we assume, so that, actually, I'm not going to use dashes, we assume that molecules are point particles, identical, the collisions between molecules are elastic, and also between the walls, okay? No forces are exerted on the particles. We have large numbers of particles. What else? And also time for one collision is higher than time between collisions. And I'm going to explain what this is in a moment. And I'm going to also write down that note that higher temperature means higher speed, more collisions, and higher pressure. Let me make a correction. Okay, here I mentioned that one of the conditions to derive the ideal gas law using a microscopic approach is that the time for one collision is higher than the time between collision. Actually, it's lower, okay? And this is an important point. And before we talk about the proof of this equation, before we provide the proof, let me show you what we mean by that. So let's say that I have a cylinder, okay, and I have some gas particles, okay. So the time for one collision will be, okay, let's take this guy, and maybe he comes here and bounce off of this guy, okay. So the time for one collision is that. Time for one collision means the duration of the collision. Whereas time between collisions, so you see how this takes an infinitesimally small amount of time, whereas the time between collisions is the time needed for this guy to, actually let's use the same guy. So it's the time needed for this guy to travel from here to meet another free particle and collide with it. So that's the time between collisions, is the time needed to find a particle and collide with it. Okay? So the denser the gas, the more frequent the collisions will be, so the lower this time between collisions will be. But in general, the time for one collision is instantaneous because it's the time needed for two particles to interact with each other and bounce off of each other, just like in a billiards ball, in a billiards table or something like that. Whereas the time between collision is higher because the time needed for that, if we take the billiard ball again, for that billiard ball to travel from point A to point B and meet the other ball and collide with it. So with all these things hopefully cleared out, let's provide the proof. And I'm going to write it here that it's optional. You don't need to know how to prove this, but it's educational to actually know how to prove things in physics. So let's start with a cube of side A. So let's assume that we have this cube, okay, with sides A, okay. So this side is A, therefore this surface area is A squared, and the volume is of course A cubed, okay? Now let's assume that inside that cube there is a particle traveling in a straight line in the x direction, and in the way we drew this axis, yeah, so this is the x, I guess, this is the y, and this is the z direction, okay? So this guy travels with velocity v, and we assume that it bounces elastically off of the walls. So if it bounces elastically, it will come back with a velocity minus v and then bounce off of this wall again and travel to the opposite direction with velocity v, etc. So to prove the ideal gas law, we assume that all collisions are elastic, including the collisions between particles and the collisions between the particles and the walls. So there is no loss of kinetic energy pretty much, okay? So what is the definition of pressure? Pressure is force over area, right? But the area in this case is 1 over a squared, okay? So we take these particles moving in the x direction, so they only move in the x direction. So imagine that if we come to this axis here, okay, so we have particles moving in the x direction along this box, inside this box. So all the particles travel in the x direction, okay? So since they bounce off of this surface area here, the surface area in the pressure definition is 1 over a squared. What is the definition of force? Delta P over delta T, right? Because the force is going to be provided by the particles colliding on that surface area, okay? But remember when we dealt with impulse, if we have a particle bouncing off a wall, the total change in momentum is 2mv, right? So 2mv over a squared delta T is the pressure exerted by all the particles traveling in the x direction, okay? Now let's move on. I hope this makes sense. Okay, now we showed how pressure is force over area, 1 over a squared delta P over delta T. Delta P is 2mv over a squared delta T. So how frequently does a particle collide with this wall, this one, okay? This is the key to finding delta T. So the particle travels 2a, so 2 times the length of the cube of distance in time delta T. So delta T gives you how frequently a particle will collide with the wall. So let's draw the wall again. Oops. Sorry, let me redraw it. These are the technical difficulties, guys, of making notes on an iPad. Okay. So this is the wall we are interested in, and we have a particle that travels with velocity v. So it will hit the wall, come back, hit this wall, and come back and hit this wall. So how frequently this wall is hit depends on the time needed for this particle to go back and forth. So what is velocity? The velocity is equal to length over time. So in this case, 2a over delta t. So this delta t that we are looking to find is equal to 2a over v. So if we plug this into here, we will find that P is 2mv times v over 2a over a squared. Did I mess something up? I don't think so. So we have mv squared over a cubed. Okay, so this is the volume and this is the velocity. Okay, don't confuse these two. So we just proven that P times the volume, if I take this a cubed to the left hand side, is equal to m times the velocity squared. And I'm using u now, guys. So u is the velocity. Okay, I just want to avoid confusion. Actually, okay, I'm gonna use this v. So I'm gonna try to make it tiny. So v squared, v is the velocity of the particle, whereas this big v, maybe let's make it have those lines there to distinguish it. So P times V is m times V squared for one particle, okay? For one particle, okay? Remember that we started with the assumption that the pressure on the wall is due to the collisions of particles on that wall, and using just classical mechanics, we arrived at this PV equals to mu squared. But, okay, this is for one particle, but we have n equal to about 10 to the 23 particles, okay? In general, we have a large number of particles. So we have that P1V, so the pressure of the first particle times V is mv1 squared. P2 times the volume, so P2 is the pressure of the second, due to the second particle, is m times v2 squared, and so on and so forth. If we have n particles, the pressure on the wall due to the nth particle is Pn times V equal to mvn squared. And if I add all these things up, what I get is, we get P1 plus P2 plus dot 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 plus Pn equal to times the volume of the cube equal to m, where m is the mass of one particle, times v1 squared plus v2 squared plus dot 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 plus vn squared. Okay, and we define that in the x direction, vx squared, the average velocity squared, is v1 squared x plus v2 squared x dot 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 plus vn x squared over n to be the average velocity in the x direction, because remember that these velocities, actually I should have written it as x, they refer to the x component of the velocity, because the motion is only in the x direction, okay? So this should be x, this should be x, and this should be x. I hope this makes sense. Therefore, if we add these pressures up, we're going to find the P total in the x direction. So P total x. By the way, pressure doesn't have a direction, guys. I mean that this is the pressure on the wall, on this wall pretty much, okay? This wall that we examined, okay? So P total x is equal to the mass of one molecule times the number of all molecules times the average speed squared of the molecules in the x direction. Similarly, we can prove using the exact exact same logic that P total, by the way, I forgot to multiply with the volume here, okay, times volume, okay, so P total Y times volume is equal to the mass of the particles times the total number of particles times C Y squared, and P total on the walls in the Z direction times the volume is mass times number of particles times CZ squared. Therefore, if we add this up, we find 3 times P times V, and this is because P total in the X wall is equal to the P total in the Y wall, and it's equal to the P total in the Z wall. This is a scalar quantity, so we can add it up. So 3 times P times V is M times N times CX squared plus CY squared plus CZ average squared. Okay. Also, which shows us, let me think, sorry for the confusion. So P times volume is 1/3 the mass of one molecule times the number of molecules times C squared, where C squared is CX squared plus CY, plus CY squared plus CZ squared. I hope this makes sense. This is the proof. Okay. Also, another thing, since 1/2 mc squared is 3/2 kT for one molecule, then we find, then the total energy of the gas is N times 3/2 kT. Okay, and this is the total internal energy of a gas, pretty much. Okay, we have, and because, and this is, I'm gonna write it here, note that a gas only has key E. Okay, and key E, the kinetic energy, is N times 1/2 m times the average velocity squared. Therefore, it's N times 3/2 kT. Okay, and this is the hardcore proof. You don't need to know about these things. You don't need to know how to derive this proof, but you need to know the formula, right? And the last thing we need to talk about in this discussion about gases is the Maxwell-Boltzmann distribution. So if we plot the number of molecules versus the speed, and speed is equivalent to energy in gases, okay? So if we plot the number of molecules with respect to their speed, we will find that very few molecules, actually 0 molecules, have 0 speed, and then you have some molecules having a higher speed, higher, and we will pretty much find something like this, okay? This is what we mean by distribution. So this is the most probable speed, most probable V. So most molecules have that speed. Then somewhere there is the average speed, and somewhere there we will find the root mean squared velocity, okay? And this plot is for oxygen 16. So let me try to help you make sense of this. By the way, if I plot the same velocity distribution for helium-4, we will find something like this, okay? So what that means is that helium-4 in general has higher speed than oxygen. So this is helium-4. So the lighter the gas, the faster it moves. So for example, so this means that if we take this speed here, okay, So what this plot shows us is that if we take this speed there, maybe that speed is 100 meters per second. It's an arbitrary value, okay? Then we will find these many molecules. If we take this speed, which happens to be the most probable speed, we will find these many molecules. If we take this speed, which is a really, really, really high speed, we will not find a lot of molecules having this speed, and so on and so forth, okay? So when we deal with the ideal gas law in the microscopic form, I mean, when we deal with PV, sorry, let me use black. So when we use PV equal to 1/3 times the number of particles times the mass of one molecule times c squared, it's useful to know the molar mass of gases. So molar mass of gases, okay, this comes handy to know. So the mass of hydrogen 2, sorry, the molar mass is denoted with a capital M. So molar mass is equal to 2 grams per mole, which is also known as 2 times U. And this is for one molecule, okay? So one molecule of H2 has molar mass of 2U. And now 1U is 1.66 times 10 to the negative 27 kilograms. Therefore, one molecule, so one molecule of hydrogen 2 weighs 2 times 1.66 is, I can't do math. Let me, 1.66 times 2, 3.32. 3.32 times 10 to the negative 27 kilograms, okay? So this is the way to work with molar masses. If they give you the molar mass of 4 helium, they will tell you that it's 4 grams per mole, which is equivalent to 4U, okay? Similarly, for nitrogen 2, the molar mass is 28 grams per mole, therefore it's 28U. And let me give you one more. Oxygen 2, by the way, nitrogen 2 is written like this, sorry. So the molar mass of oxygen 2 is 32 grams per mole, or 32U. Now, if you want to work with the number of moles, so for 1 mole, actually, let me write it as for n equal to 1 mole of, say, hydrogen 2, we will have 2 grams of hydrogen 2. So what I'm trying to say is that 1 mole of hydrogen 2, if we look into this molar mass, I told you that the molar mass of hydrogen 2 is 2 grams per mole. So if I have 1 mole of hydrogen 2, it weighs 2 grams. I hope this makes sense. Similarly, 1 mole of helium 4 weighs 4 grams, and so on and so forth. So yeah, that's it. This is what I wanted to mention. So because, you know, you will need to use PV equal to nRT, or maybe you will need to use PV equal to 1/3 times the number of particles times the mass of one molecule times the average speed squared. Then to find the mass of molecules, you use this methodology I mentioned here. So that's it for gases. I hope all this makes sense. If you guys have questions, let me know in the comments. And I hope this is helpful. Please share with your friends, subscribe, etc.